Hey guys, today we are looking at scatter plots and lines of best fit. So, looking at back at our data from yesterday when we were graphing our stuff on Desmos with our height versus shoe size thing, we tried to come up with a line of best fit. And we did that by making a slope-intercept form of a line, dragging our sliders, adjusting that to make it look like the best line that we could. So, based on what we did, we were kind of guessing and coming up with what we thought was the best answer. So, for now, is there only one correct answer? No, we can say there's multiple lines that will work. And what we're going to get into eventually here in the next few days is talking about how we can come up with that best line of fit. And how that ties into what we're talking about is this idea of creating an equation to represent data. So when we made our graph of our height versus shoe size, we were using what was called bivariate data, or in other words, data that had two variables. Okay, bi, of course, meaning two. And what we do with these equations that we create then is it allows us to either interpolate or extrapolate information from that graph. So interpolation, inter meaning inside, allows us to predict values that are going to happen within a range of data. So let's say we had a bunch of points on a graph or a scatter point, and maybe it looked kind of like this. Well, there's a huge hole inside, and maybe I want to figure out, well, what would be represented by this? So using this line of best fit allows us to guess at what those points should be in the middle. The other one then is linear extrapolation, extra meaning beyond. So this is what we use to predict data values on the outside of our data range. So this is probably the most common, is we'll see data that maybe looks like this, and now we want to create a line to figure out, okay, what's going to be happening out in the future. So we can break these types of correlations down a little bit farther into three types. So we can say data is positively correlated. So positively correlated data is data that if and only if the line is drawn through the data has a positive slope. So that just means that our data points, okay, have a roughly linear relationship, and that relationship is going uphill. So examples of things that we've seen, well, the one that we did in class, height versus shoe size, would be an example of something that's positively correlated. Okay? Meaning the taller you are in general, the larger your feet or the bigger your shoes are. Okay? Other examples would be maybe the more time you practice something, the better you are at a skill. Okay? The more, so as one goes up, the other goes up. Practice time increases, skill level increases. So negative correlation then is correlation where when you draw your line, okay, or through all of your data points, the line that you would draw is going to have a negative slope. Okay, so it still kind of roughly looks like a line, right? It's just that now the slope is negative. So negatively correlated data are things where as one goes up, the other increase or decreases, or as one decreases, the other goes up. So an example for this, especially this time of year, would be temperature versus heating cost. Okay, so as your temperature drops, your heating costs are going to rise. This would be a negative correlation. And the last type of correlation we talk about is, well, no correlation at all. So what this means then is that if you have your set of data, and maybe mine looks something like this on the screen here, there is not a line that's going to fit better than another one. So kind of how I think of that is that if I were to look at this graph here, if I drew a positive line or if I drew a negative line, neither of them are really better than the other. So this means that there's no correlation, or in other words, there's no relationship between the things that we're trying to compare. Okay? And that's the big idea there. There's no relationship between our data. So examples of no correlation would maybe be, the amount of sunshine and whether the Vikings are going to win on Sunday. Or maybe your height compared to your algebra grade. So those are things that have no impact on each other. So if you were to graph those results, you're not going to find any data. The last thing we want to talk about is how we can create a better line of fit. So as I mentioned earlier in the video, when we did our height versus shoe size, we kind of just grabbed some sliders and tried to make one that looks good. Well, we have one way that we can do this algebraically to make it a little bit better. And how we can do this is try and find a couple points that we think represent our graph and create an equation from there. So maybe I want to choose this point here, and I'm going to choose this one here, because I think if I draw a line through these, it's going to be pretty well representative, or a pretty good representative of the data that I have. So what are my ordered pairs? Well, this one right here would be an ordered pair, -1, -7. And then this other one that I chose here is at the ordered pair 2, 6. So now I can write an equation of this line. So again, to do this, well, anytime I'm writing an equation of a line, I have to find my slope. So to find my slope, I can find the difference in my x values, or excuse me, the difference in my y values divided by the difference in my x values. So here I would get 13 over 3. Not a nice number, but that's okay. And then I'm going to use one of my points. So I'm going to use this one. It doesn't matter which one. So now I can create my equation of my line using the slope that I found. So I'm going to do point-slope form because I have a slope and a point. So y minus my y value equals slope times x minus my x value. So now to solve, to put this in slope-intercept form, I would distribute. So I would get 13/3 x minus 26/3. And then I could add 6 to both sides. Well, adding 6 would be the same as adding 18/3. So now I end up with y equals 13/3 x minus 8/3. And that's what we're doing today.